first 4 questions are graphing. There's similar methods of graphing both exponential and logarithm. Question 1 is an exponential function. The way this was presented, really 3 steps, I guess. The first step is to locate the horizontal asymptote. That's found from the vertical translation here of -1. That means the horizontal asymptote moves down 1 unit. Step 2 is to locate the y-intercept. That's found by letting x equal 0. So we put a 0 in for x. 0 minus 1 is -1. 3 to the -1 is 1/3. 1/3 minus 1 is -2/3. That's about right there. Third step is to find 2 other points on the graph. So if x equals 1, for example, 1 minus 1 is 0. 3 to the 0 power is 1. 1 minus 1 is 0. So 1, 0 is on the graph. If x equals 2, 2 minus 1 is 1. 3 to the first power is 3. 3 minus 1 is 2. So there's the graph. Now it doesn't specifically ask for it on this question here, but it may on the exam, the domain and range. The domain is all real numbers. The range doesn't include -1, but it's from -1 to infinity. Okay, question 2. Same 3 steps. Locate the horizontal asymptote, locate the y-intercept, and then find a couple other points. Same thing, we have a vertical translation here, down 1 unit, so the horizontal asymptote is located at -1. Y-intercept is found by letting x equal 0. Place a 0 in there for x. 0 minus 2 is -2. 1/3 to the -2, let me write that up here. 1/3 to the -2 is the same as 3 squared, so that's 9. 9 minus 1 is 8. So 0,8. Now, we let x equal 1. 1 minus 2 is -1. 1/3 to the -1 is the same as 3 to the first power, so that's 3. 3 minus 1 is 2. 1,2. Then if we have a 2 for x, 2 minus 2 is 0. 1/3 to the 0 is 1. 1 minus 1 is 0. Even though these are both considered exponential functions, question 1 is an exponential growth function, question 2 is an exponential decay function. Here the domain is all real numbers. The range is -1 to infinity. Okay, the steps are similar for graphing logarithmic functions, but instead of locating a horizontal asymptote, we're locating a vertical asymptote. The vertical asymptote is found by following the horizontal translation. X plus 1 is a horizontal shift to the left, 1 unit. Then we locate the x-intercept. That's found by letting y equal 0. Now f of x is really the same thing as y. So if we put a 0 in for y, we have to solve for x to find out what the x value is. We're going to add 1 to both sides. That gives us the equation 1 equals log base 3 of x plus 1. If you exponentiate both sides with a base of 3, that takes care of the logarithm over there. 3 to the first power is 3, so we have 3 is equal to x plus 1. That means that x is equal to 2. So the x-intercept is 2. Now we're going to do the same thing that we did up here. We're going to find a couple of other points. It might be easier with logarithms, instead of choosing the x values like you normally would, to choose the y values. For example, if you choose the y value of 1, you're going to get 1 right here. If you add 1 to the other side, you're going to get 2 is equal to the log base 3 of x plus 1. Exponentiate both sides, you get 9 is equal to x plus 1. So x is equal to 8. we could let y equal -1 here. You can see what happens. So if we add 1 to the other side, we get the equation 0 equals log base 3 of x plus 1. Exponentiate both sides. We get 1 is equal to x plus 1. That means that x has to be 0. So there are a couple of points we can plot. 8, 1, 0, -1. Here the domain is from -1 to infinity, and the range is all real numbers. It doesn't include -1 because that's where our vertical asymptote is for the domain. Okay, question 4. Vertical asymptote is located by following the horizontal translation. X minus 2 is a movement to the right 2 units. Now we need to find the x-intercept by letting y equal 0. So we place a 0 right in here. If you add 2 to the other side, you get the equation 2 equals log base 2 of x minus 2. Exponentiate with a base of 2 on both sides. 2 squared is 4, so we have 4 equals x minus 2, x equals 6. So there's the x-intercept. We want x to equal negative, or we'll let y equal -1 here. So we put a -1 in place of y. Add 2 to this side and get the equation 1 equals log base 2 of x minus 2. Exponentiate with a base of 2. 2 to the first power is 2. 2 equals x minus 2. That means that x equals 4. So we have 0.4 comma -1. If we let y equal -2, and the reason I'm choosing smaller y values, if I let y equal 1, it would be a point way over here on the x-axis. So you can graph it if you want, but I'm choosing some smaller values of y to get smaller values of x. So if this is -2 for y, and you add 2 to the other side and you get 0 equals log base 2. X minus 2, exponentiate with a base of 2. 2 to the 0 power is 1. 1 equals x minus 2. So we get an x value of 3. So the domain here is from 2 to infinity, not including 2. The range is all real numbers. Okay, this next section is pretty easy, just rewriting. If it's in logarithmic form, you can exponentiate using the same base. So you have 216 equals 6 to the third. Here you use a base of 9. So that's gone, and you have 81 is equal to 9 squared. Here you can use a base of 13. So that's gone. You have 1 is equal to 13 to the 0 power. Here you use a base of e. You have 155 equals e to the x. The next section is just doing the reverse. They're already in exponential form. So you have to rewrite using logarithmic form. To cancel that base of the 2, you have to use a log base 2 on both sides. That's gone, so you have 6 is equal to the log base 2 of 64. Here you use a natural log. So you have x is equal to the natural log of 216. Here you use a log base 289. So you have 1/2 equals log base 289 of 17. Here we're going to use log base 8. 2/3 equals log base 8 of 4. So now this next section is evaluating logarithms using properties of logarithms. One of the properties that we talked about is, regardless of the base of the logarithm of 1 is always equal to 0. Log base 16 of 4. The trick here is to try to get try to change the 4 into 16 to some power. So log base 16, 4 is the same as 16 to the 1/2 power, because the power of 1/2 is just a square root. The square of 16 is 4. Now that we have matching bases, the answer is 1/2. We're in 15. We have to change 125 into 5 to some power. 125 is 5 to the 3rd power. Those bases cancel, so the answer is 3. Here, similar trick as in question 14. We're not going to change the base of the logarithm. We're going to change the 5 into 25 to the 1/2. 25 to the 1/2 is just the square root of 5, or square root of 25, which is 5. Now that they have matching bases, you get an answer of 1/2. A base of 3 and a log base 3 are inverses. Those just cancel each other out, so the answer is 8. Same thing, natural log is just a log with a base of b. Those have the same base, so the answer is 5. Next section here, use the definition of logarithmic function to find x. Essentially all they're doing here, all I'm asking you to do is to solve the equation. If we exponentiate using a base of 12, then we have x equals 12 squared, which is 144 here. If you exponentiate with a base of 6, then you have x is equal to 6 to the negative 1 power, which is 1/6. Over here, if you use a base of 4, you have x is equal to 4 squared, which is 16 here. So it's a little trickier. You're going to have to use a base of x. So we have 3 is equal to x to the 1/3. We use a power of 3 on both sides, and those powers cancel each other out, so x is equal to 27. Okay, condense. First of all, when you're condensing, you want to look for numbers in front of logarithms. Now this one's kind of hard to spot, but dividing the entire logarithm by 3 is exactly the same thing as multiplying the expression by 1/3. So that's also a number in front. So these numbers have to go back up top as exponents. So this is the log base 4 of y plus log base 4 of z to the 5th plus log base 4 of x to the 1/3. Now since all 3 logarithms are adding together, we can condense this using multiplication. So all of those terms have to multiply. Y times z to the 5th times x to the 1/3. Question 24, start the same. All of these numbers in front of the logarithm have to go back up as exponents. So this is going to be the log base 4 u to the 5th minus log base 4 of w to the 5th minus log base 4 of v to the 10th. Now you got to take 2 logarithms at a time. These first 2 logarithms, there's a minus sign separating them, so when you condense just those 2, that's going to be the log base 4 of the quotient u to the 5th over w to the 5th, then we subtract log base 4 of v to the 10th. Now we have to condense these 2 logarithms. There's a minus sign between them. That means these 2 expressions have to divide each other. So it's going to be the log base 4 of u to the 5th over w to the 5th. And now we need to divide v to the 10th. Well, dividing is the same as multiplying by the reciprocal. So v to the 10th is actually going to be on the bottom. Okay, 25. 25 is a rather tricky one. Logarithms and radical signs don't play nicely together. That's just something that you'll be best to try to remember. Radicals and logarithms don't play well. Change radicals into rational exponents. So this expression could be thought of as that. A square root is just the power of 1/2. Now, if you distribute this exponent to the numerator and to the denominator, this becomes the log base 5 of x to the 1/2 over y to the 1/4. And you have a power that's being raised to another power you multiply. Now, since we're taking the logarithm of a quotient, we can expand that using subtractions. This is log base 5 of x to the 1/2 minus log base 5 of y to the 1/4. And you move the exponents down to the front and you get 1/2 log base 5 of x minus 1/4 log base 5 of y. Now in 26, we have a couple things going on. We have a quotient, but also we have a product down there at the bottom of the quotient. So we need to expand the quotient first using subtractions. This becomes the log base 4 of 8 to the 6 minus log base 4 of CB to the 3rd. Now we have to expand this product here, and keep in mind we're subtracting the entire expansion. So this is log base 4 of 8 to the 6 minus. Now put the expansion in parentheses. Log base 4 of C plus log base 4 of B to the 3rd. Two things we have to now do: move the exponents down to the front and distribute this minus sign right here. So this is 6 times log base 4 of A minus log base 4 of C minus 3 times the log base 4 of B. Now we're getting into the solving equations. For logarithmic equations, you have to isolate the logarithmic term and then exponentiate both sides. So this is the logarithmic term of this equation. So we have to divide by -3, and we get the equation log base 2 of b minus 7 is equal to +3. Now you exponentiate using a base of 2, because our logarithm has a base of 2. So you have b minus 7 is equal to 2 to the 3rd, which is 8. Add 7 to both sides and you get b equals 15. Over here, the natural log is already isolated. There's nothing in front of it. There's nothing outside of the function. So we can go ahead and just exponentiate using a base of e. E and the natural log are inverses. So you have x minus 1 equals e to the 3rd. Add 1 on both sides and you get x equals e to the 3rd plus 1. And 30 are different types of problems because they have multiple logarithms. So this, for example, needs to be condensed into one logarithm. Same with this. This expression needs to be condensed into one logarithm. So the two logarithms have the same base. That's important. There's a plus sign between them. That means when we condense, these two expressions multiply. So this is log base 5 of x times x plus 6. And that equals a log base 5 of 55. Now that you've condensed, you exponentiate using a base of 5. So that just cancels each of the logarithms. So you have x squared plus 6x equals 55. If you subtract 55 to the other side, it's going to equal 0. If you factor x plus 11 and x minus 5, which means that x equals negative 11 or x equals positive 5. Now you always got to check, remember you can only take a logarithm of positive expressions. That doesn't mean that x can't be negative, but what that means is when you plug it into the expression, it has to become positive. If you plug in a negative 11 right here, or if you plug in a negative 11 right here, you would end up taking the logarithm of the negative number. That's an extraneous solution. The only one that works is x equals 5. Here on 30, they have the same base, and there's a plus sign between the two logarithms. So when you condense this, these have to multiply. It's 5 times x plus 10. That equals 2. Exponentiate both sides, and you get 5x plus 50 equals 81. Subtract 50 and you get 5x equals 31. Divide by 5 and you get x equals 31 fifths. Now we're to exponential equations. Similar type of method, you isolate the exponential term and then take a logarithm on both sides. So this is the exponential term. There's nothing in front of it, nothing behind it. It's already isolated. So we're going to use a log base 8 on both sides. Log base 8 cancels a base of 8, so x is equal to the log base 8 of 35. Now in 32, this is the exponential term, 2 to the x, so we have to divide by the 3, we get 2 to the x is equal to 9. Now we can use a log base 2, so x is equal to the log base 2 of 9. 33, this is the exponential term right here, so we have to add 8. We have e to the n minus 10 is equal to 30. Now we cancel e with using a natural log, so n minus 10 is equal to the natural log of 30. And you add 10 to both sides and get the natural log of 30 plus 10. You cannot combine that to make 40. 30 is inside of the function, the 10 has to stay outside the function. 34, this is the exponential term right here, so divide by 8. We have 8 to the x plus 3 is equal to 3. Now take a log base 8. Those are gone. X plus 3 is equal to the log base 8 of 3. Subtract 3, subtract 3. You must not subtract this 3 from the 3 that's inside the function. Those have to stay separate. So x is equal to the log base 8 of 3 minus 3. Now, this is compounded continuously. This is continuously compounding interest. The formula is a is equal to the principal times e to the rate times time. $5,000, that's the principal investment. And right here, this is the rate, 0.06. It's asking for how long would it take. That's a t. That's searching for t. T is an exponent. The only way to solve when a variable is an exponent is to cancel the base. So this is going to involve logarithms. Now, the principal is 5,000. The rate is 0.06, and we are trying to find out how long that's going to take. And we're trying to find out how long it's going to take to double. So 5,000 is going to become 10,000. If you divide by 5,000 on both sides, you get 2 is equal to e to the 0.06 times t. If you use natural log here, you can have the natural log of 2, and those natural log and e are inverses. They 0.06 times t. You divide by 0.06, and the time it takes is the natural log of 2 divided by 0.06. Unfortunately, since we aren't allowed to use calculators, that's how we have to leave the answer in exact form. Now, question 36. The formula for this function is very, very similar to this one. It's the amount at any given time t, which is what they're searching for. Find a function that models the number of bacteria at any time t. So it's a of t is equal to a sub 0, which is the initial count, times e to the kt, where k is the growth factor, a sub 0 is the initial, t is time. Now it starts with 10,000, that's our a sub 0. Now, what they haven't given us is the growth factor. We have to first solve for the growth factor before we can finish this function. Now, it says that 10,000 becomes 20,000 in 40 minutes, so we're going to allow time to equal 40 minutes. Divide by 10,000 on both sides, you get 2 is equal to the e to the k times 40. Take a natural log on both sides, and then divide by 40, we get the value of k, it's the natural log of 2 over 40. Now that we know the value of k, we can finish our function. The amount at any given time t is equal to 10,000, that's the initial amount, times e, this is our k value, and that's multiplied by t.